Hello, and welcome to the demonstration of my individual project titled Tracking Individual Players in Commercial Rugby Footage. This demonstration will be broken down into sections. The first will discuss the motivation behind the project, the second will give a brief outline of the project aims and the software that was developed. Next will be the design, which will be further split into subsections pertaining to the methods used for detection, tracking, and identification. Having played rugby for nigh on a decade now, this project really jumped out to me. Coaches spend quite a considerable amount of time analysing game footage in order to come up with and judge the effectiveness of different tactics. Many tactics rely on the running lines of the attack and the defence. For example, a defensive line could opt for a blitz defence, where the line moves up straight, or a drift defence, where the line is diagonal. Both have their merits and will be more or less effective against different attacking lines. The aim of this project was to help simplify this analysis by tracking player paths on a clear representation of the pitch. This project involved developing a piece of standalone software capable of taking a piece of commercial footage, performing the required computation, and demonstrating it in some manner to the user. The Python program makes use of tkinter for UI purposes, as well as a number of other libraries such as OpenCV and Keras for the actual computation. The design of the system is rather simple when viewed from the high level. A video is just a sequence of frames that can be iterated through, so we can think of the system from the perspective of a single frame. The frame is passed to a number of components. The scene detector, which determines whether we've changed from one scene to another, thus allowing the system to deal with non-continuous footage such as highlight videos. The player detector, which picks out players from the frame by making use of the YOLO v3 model described later. The line detector, which identifies pitch lines in the image which can be used to identify the position on the pitch. And the number detector, which attempts to identify and recognize numbers in the frame which could subsequently be used to identify players. Following from this, the player and line detections are fed into a homography transformation which uses the information to determine each detected player's position in the pitch representation. Those positions and the result of the scene detector are then fed into the particle filtering component. Each of the filters are updated as required. The reason for feeding in the results of the scene detector is that the filters need to be reinitialized when the scene changes. The frame then has any relevant annotations drawn on it and is given as output. I will now go more in depth with each component. It made sense to categorize the components based on whether their task was detection, tracking, or identification. Starting with detection, there are three main parts to look at: player detection, line detection, and scene detection. The player detection works on picking out players from a frame. It makes use of Redmond's YOLO v3 model, which runs faster than other well-known models such as RestonNet 50 and FastRCNN, but does come with a slight accuracy trade-off. The speedup is due to the fact that it makes use of a single convolutional network for all the separate components of object detection, essentially treating it as a regression problem, as opposed to using multiple networks for region proposal and object classification. The line detection makes use of a Hoff transform in order to extract pitch lines. In order to reduce the noise, the frame is first pre-processed. Pre-processing consists of using a series of filters and background subtractions, which are used to extract a binary image. First, a histogram of hue values is generated, and the most common hue is used to generate a mask, which should hopefully exclude the crowd. This is using the assumption that the most common hue will be the pitcher's colour. A morphological closing operation then helps to reduce incorrectly classified regions of the pitch. This is followed by a medium blur, and finally a background subtraction of the filtered image from the original. Unfortunately, the line detector was quite a weak component, with a number of missed, duplicated, or incorrect lines, as shall be seen in the later demo. The scene detection is based on Zorner's perceptual hashing. An implementation of this is built into an OpenCV module, and returns a value representing the difference between two frames. This result is compared to a threshold to determine whether the scene has changed. Moving on to tracking, this is done by making use of a particle filter. A particle filter uses a number of particles to try and predict the next state of the system. When the next state is observed, it assigns weights to the particles based on how close it was. It then removes certain particles that are unfit and initializes some new ones. The system is quite robust to temporary occlusion, as many of the predictions are done using a Bayesian layer. The tracking system also makes use of a decay function to remove unused filters, thus reducing filter explosion. Lastly, the identification of players was intended to be done via detection of jersey numbers, which would then be associated with the relevant filter. The system uses two neural networks. One works on detecting a number's location, and the other works on identifying what number it is. The detector lets down the classifier, quite badly. As the detector is only able to identify one region where a number may be, this is likely due to the training data that was used and would have been tested and hopefully corrected if time had allowed. Now that the project has been explained, I shall give a demonstration of it. As you can see, there is a frame output to the left, a pitch representation in the top right, and a number of annotation toggles, and some useful information is given in the bottom right. A lot of these toggles are self-explanatory, but I will point out that the homography translations represented by magenta circles are for current observations given by the homography transformation, and particle filters, which are represented by either red or blue circles, represent the mean of the predictions. We use the two different colours of circles on the particle filters to represent whether it is using the Bayesian layer or whether it is an accurate prediction using actual observations. We use blue for when using the Bayesian layer, and we use red for when we're using actual observations. You can clearly see the effectiveness of the YOLO v3 model at detecting players. The line detection problems can be seen with missing detections and duplicates. And the failure of the number identifier is evident. When the scene changes, an indicator is shown. The speed of analysis is far from real-time, but does run within what was deemed to be reasonable. That is pretty much all I have to show you, so thank you very much for watching my demonstration.